Yeah, so one point we haven't stressed enough, I guess, is that synthetic algebraic geometry also works if you start constructively, even when you construct your Zariski topos and things like this. We can do this constructively. And what you also can do is you can start and constructively repeat Hartshorne chapter 2, which makes it more complicated. Like, can you find sheaves on something like a topological space, maybe more detailed soon, and define what an affine scheme is, and in the classic way, but done everything constructively. And now you could ask a question, namely, is the functor of points approach constructively the same as the Hartshorne chapter 2 approach, like Grothendieck's approach to schemes? And this is what Max is working on. So I'm interested to see what we will learn in this direction.
Yeah, thank you. I think that's the title that you put on the website, right? Something like it. But let me start by thanking the organizers. Great opportunity. And so what I'm presenting today is not really synthetic algebraic geometry, but actually figuring this story out helped me a lot, understanding what is going on in the synthetic setting. So as Felix said, there are basically these two ways to do basic algebraic geometry and introduce schemes. Well, you start with the category of commutative rings. And you take the opposite. And this is what affine schemes are supposed to be, right? So if you're only interested in affine schemes, you could just define this category and take an up. But then you want to introduce schemes which are, in a sense, I would say a nice co-limit of these affine schemes. So you have to embed this category into a bigger category, a co-complete category where, well, yeah, where your schemes are supposed to live. And I guess the functor, oh, maybe that's not the other way. The odds are that when you took your algebraic geometry class, maybe unless you learned algebraic geometry in Augsburg, but else you take the category of locally ringed spaces. Oh, okay, let's give it a name. Locally ringed spaces, and this is functor spec, and then you what you have, well, locally ringed space, topological space with a sheaf of rings such that the stalks are local, right? So when you want to introduce this functor spec, you look at the set of all prime ideals of your ring R, with together with the Zariski topology, and structure sheaf. Let's call this OR, that on the basic opens of the Zariski topology gives you this bring localization away from particular element, and then you compute the stalks. So OR at some point P, which is a prime ideal, is R localized at that prime. That's local. So this is quite a lot that you have to do, right? On the other hand, if you do this functor of points approach, you look at functors from commutative rings. And then the fully faithful embedding here is just unida. So I'll use SP in this talk to differentiate from this spec, and this is I guess this is the notation that's used in De Mazur Gabriel, which is like the main reference for developing the theory of schemes on this side of the picture, but they are actually closely connected. You have an adjunction here, and this one is the easy one. That's just morphisms of locally ring spaces. Back four. So you plug in a locally ring space here, and then you get the functor that takes a ring and plugs it in spec here. And in the other direction, you have something which we call the geometric realization functor. I don't want to give the details now. I'll give the details of the constructive analog later. And you have this adjunction, which, so schemes are locally ring spaces that have a covering by specs. Schemes here are or presheaves on covering up. I don't know why I put an S here. Covering up that have an open cover. So you also have to define what an open subfunctor is in this presheaf category. And this adjunction takes sort of the geometric schemes to the functorial schemes and vice versa. Classically, modulo some size issues. You have this left adjoint by abstract nonsense. So this comes from the left Kahn extension of spec along unida. And what I want to show today is how to recover this picture constructively. In particular, we have to give a constructive analog of this story and then look at what this adjunction looks like in a constructive setting. And this will actually give us a lot of familiar objects in here that appear in synthetic algebraic geometry. So some stuff like open propositions that Matthias talked about, those will appear in this adjunction. And maybe in some historical remarks about constructivizing this story. So I would be very thankful if people have more literature or know more about this, but my impression is that the constructive community always assumed that this would be the easier part, the easier side to constructivize, because you have a bunch of problems here. First of all, topological spaces you want to avoid. You want to do point-free topology. And this also makes it hard to talk about stalks. So what even is what even is the right notion of sheaf of local rings? So there's a whole range of issues to overcome. Whereas here, everything seems to be fine and is already point-free by construction. So the way you constructivize this is you don't look at the set of prime ideals, but you look at the open sets as your basic as your basic objects, and actually you only look at the compact open sets. So you can define basically quite quickly and this is the bounded distributive lattice. I'll just write lattice. Whenever I say lattice, I mean bounded distributive lattice.
Since we have a 0 and 1 for
Yeah.
the top elements.
Yeah. So this is the lattice generated by elements E of F, or F is an element of R. And well, these D of F observe some relations. Well, E of one of the one element of the ring is the top element of the lattice. E of 0 is 0 in the lattice. Then D of product is the minimum of these, and D of sum is, well, it's not equal, but it's at least less than the join of D of F and D of G. So if you're classically minded person and you like spec of R being the set of all prime ideals, then you know what this corresponds to the usual set D of F. So all the prime ideals that don't contain the element F, and sort of these relations do hold in the power set if you plug in the intersection and the union and subset relation here. But of course you can define this in a completely point-free way by saying you take the free distributive lattice generated by these elements and you mod out by these relations. You can also take quotients of you can also take the quotient of the lattice of radicals of finitely generated ideals. Quotient on finitely generated ideals. Oh, I didn't want to say that. Okay, so you can also take the lattice of finitely generated ideals modulo the relation that, so here also modulo well, ideal generated by elements A1 to AN is related to one M, and only if taking the radical of those gives you the same ideal. So those are basically 2.3 ways of giving the Zariski lattice, and then well, the structure sheaf that works the same, right? So the D of F's are generators of that lattice. You map them to the localization where you invert a single element F. And then the question becomes, in what sense is that a sheaf of local rings? And maybe also historic remark at this point. So this was done. This was done in a paper by Thierry Coquin, Henri Lombardi, and Peter Schuster in 2009. They used this construction. They did the structure sheaf, but they never said what a sheaf of local rings on a lattice is. So they could then define their constructive notion of sheaf, which coincides with quasi-compact, quasi-separated schemes, and they could define a morphism of schemes by saying, well, whenever we have a ring morphism between two rings, we get an induced morphism between the Zariski lattices that also gives you natural transformation of the sheaves the way you would expect. But they then defined a morphism of schemes, one to be that it was just induced by compatible families of ring morphisms. So because they didn't develop a notion of morphism of locally ringed lattices. So the question is, in what sense does the Zariski lattice with the structure sheaf define a locally ringed lattice, and how does that relate to locally ringed spaces? When did I start? About 5 minutes.
10 to 4?
10 to 4, yeah, okay. Should go maybe a bit fast. Yeah. It's sort of, I think the key ingredient to understand both these things is sort of this particular set of relations. And this so the key definition is call maps E from lattice L to, no wait, it's the other way around, right? From your ring R to your lattice, in this case it's this Zariski lattice, a support. Then the Zariski lattice is universal in the sense that we have our support capital D, and given any other lattice with a support small d into some other lattice. So D being a support means it also these relations also hold when you replace D here. And there is a unique morphism of lattices. Okay, but supports are also very helpful to characterize sheaves of local rings. So now we go back into point set topology, classical terrain. If you have a ring space X with sheaf OX, you can define the invertibility. So definition for a point X. Oh wait, no. for an open set U and a section S, the in the open and I used to quickly the U of X is the set of all points such that S at the stalk is a unit. So this will always be an open subset of U, and it's sort of the largest open subset where restricting the section S becomes a unit. And the proposition is so X is locally, so this ring space is locally ring space if and only if for all U du, this is now a function going from sections that U into like this. So open subsets of U, maybe like this. This and so I think this is sort of, I don't know. For me, it was when I saw this the first time, I found it kind of surprising that sort of this lattice algebra theoretical notion can be used to define locally ring spaces in a point-free way, because we only talk about opens and sections here, and to define sort of the point-free counterpart of the spectrum in a nice way. Okay, maybe proof sketch. So, well, I mean, we'll always have that. I'll just do the. Well, invertibility open of 1, that's always U itself, right? Because 1 is already a unit. And this product will also hold. So basically what we're proving is actually this is a locally ring space if and only if the other two, those two hold. And this comes from, well, a ring A is a local ring if and only if A is non-trivial, so 0 not equal 1 in A, and if I'm a bit inconsistent with my variable names, but if S plus T is invertible, then S invertible or invertible. So maybe you can already see why this equivalence holds now. So if we look at any stalk, we have two elements, such that we have two elements such that at the stalk their sum becomes invertible. That means already one of them had to be invertible, and they sort of come like from a section that below you.
So by locally ring space on the left side, you mean every stalk, so
Yeah.
every point of X something?
Yeah. So locally ring space means all of those
Rings are local rings.
are local rings.
Okay.
Yeah.
And
Since we have this algebra lemma,
yeah,
classically local ring, so ring with a unique maximal ideal. A has a unique maximal ideal if and only if it's non-trivial, and this holds. So when we work constructively, well, actually, this will be our definition of a local ring, and this will be our definition of a locally ringed space, or later locally ringed lattice. Something.
But is the equivalence here constructed when we take the constructive definition for local ring? Or did you assume anything on space X? I mean, is it solver or anything?
No, I don't think so. No, I don't think we have to.
But I
assume
mean
anything.
somehow that being a support is local. The local. I mean, you know something about your ring sheaf of rings, which is stalkwise a local ring, and whereas your support condition is a condition for each open. So somehow it seems that you need that if you have a support stalkwise.
But what is the support stalk?
Yeah, whatever it means.
Yeah.
I mean, maybe it's enough. I mean, you could, or maybe it's enough to say that something is support if it's locally support. Okay.
Yeah, I would expect that once you have the right.
I mean, whenever you have finitely many ring elements, you can and you can go to some open subset where this holds. I mean,
Yeah.
So do you think about the iteration from left to right, right? Okay. Right now, you want to prove that the thing is a support, and you have the feeling that you only have that it's locally a support.
yeah, I mean, from right to left is okay, right?
Okay.
Yeah.
Because I mean, if we want to go from the right to the left, you just take two elements S and T.
Yeah.
That sum to one,
So,
say.
yeah.
And then you have D of S plus T is D of one is everything. And this, yeah.
Okay, that's good.
And the other side you have that it's But
so from left to right, can't we start by checking that D of 0 is 0?
Yeah, this corresponds to this condition, right? So if
okay.
this test has to be empty.
Yeah.
If
Yeah,
well,
and the empty
it's a no, yeah.
set is the bottom element of the lattice.
Of this lattice
Exactly.
of
All right,
open
okay.
review, yeah.
And 0 not equal 1 in all the stalks. The support of the 0 function is empty.
Yeah. So this.
And same with the.
yeah, but I think we can.
Yeah.
Yeah, I mean.
Yeah, I mean, this was maybe a bit hand wavy because I didn't spend too much time. This is a very neat observation, but I didn't want to write it out in full detail. But exactly, so if you have du of S plus T, so this will be all the points where S plus T at that stalk is invertible. So you know
I
that
see it now.
either S at that stalk or T at that stalk is invertible. that means that that point X had to be already either in du of S or du of T. So this is, so the condition becomes,
because we define our U pointwise.
This is a subset of,
Yeah, because we are in the setting of local ring topological space.
Yeah.
Now we this is sort of just motivation or inspiration from the point world for our point-free setup.
And I don't know whether it's useful, but let me remark that both sides of the proposition are also just reformulations of saying with the Crypto semantics that structure sheaf is a local ring. And from logic, we know that locality of a sheaf of rings can be checked stalkwise, at least for those topuses which have enough points, but topuses built from topological spaces always have enough points.
And another interesting historical remark, maybe sort of this way of defining sheaves of local rings in terms of invertibility of them, that was actually already done for arbitrary locally ringed topoi, where you can also define them, by Monique Hakim in her PhD. That's back in 72. But I found this observation particularly useful for the lattice case, because supports our notion about lattices, and we're doing lattices here. So I should move on if I want to show the. So what is a locally ranked lattice then? L, and we have a sheaf OL. I mean, I didn't really say what a sheaf on the lattice is, but it's a poset, so we know what a pre-sheaf on that is. And it has finite joints. So the sheaf property, we only look at the sheaf property for these finite joints. Is locally if we have, well, we have such a support map D, that's a dependent function sort of. So now you, in this case of the Zariski lattice, is some compact open of the Zariski lattice, maps it into functions from sections at U to something in the downset of U, something lying below U, such that, well, for all U support, and it's an invertibility open, in the sense that for all U S and V less than U, V is less than U of S, if and only if that's restricted to B is the unit invertible. So the problem is, if we want to do everything in a point-free way, right? Of course we have to give this as an extra structure, but it's a property-like structure because of this condition. There can be at most one such map. Right. Yeah. If you had another map D prime with this property, then you can show that D prime and D have to coincide for all your S, because clearly if you restrict S to du of S, then it will be a unit. So, did that make sense? Okay. So maybe if you take Zariski lattice with the structure sheaf, what is the general D? So in the case of the Zariski lattice, let's say if we look at some base element D of F, and then something in the section.
Sorry, did you say that you call a local?
If it has such as,
you call a ring lattice a locally ringed lattice if it's equivalent to such a D.
Yeah, it's I think the correct definition would be a locally ringed lattice is a structure of lattice L, sheaf OL, and the D such that it holds. But I'm being a bit ridiculous because this is a property-like structure. There can be at most one such D.
But you want morphisms of locally ringed
lattices
to preserve this, right?
Yeah, exactly.
Yeah, okay.
No, it's true. Yes. So what is this in the case of the structure sheaf? Well, at basis element D of F, sections are sort of fractions. So it will be R divided by some power of F, and this will just be dr and D of F. This is the biggest element where R and F become invertible. So in particular, this general D is just the support D at 1. Yeah, and exactly. So why do we all do this? Well, as I said, we want to replace this with this by something point free. So we want to define a morphism of locally ringed lattices, and so morphism of ring lattices just reminder. This morphism of this is the lattice from homomorphism from L to M. And this is a natural transformation from OL to like cos. No, wait, yeah. So if it's up, maybe replace M and L, so OM to pi loss dot L. Yeah, let's say okay, so pi sharp at some U is the ring morphism from OLU to OLU, OL pi of U. So, I mean, we end up in the situation where things are opposite as compared to working with spaces, because, I mean, and we think of the lattice elements as the compact opens of our space. So this pi will actually be like taking the pre-image of our continuous quasi-compact map.
And all the arrows that you've drawn here go in the algebraic direction.
Yeah, exactly. This is really in distributive lattices. Yeah. So this is
I think I missed something on the left-hand side, so. In the last line, I mean, this you can take as the definition of du of S. Right?
Yeah. So it's, if you give yourself,
But you asked that such a thing exists.
Yeah, okay, this
Yeah.
would be the axiom, but now you said, well, it has to be respected by morphisms, but I mean,
But that's what you did you want to write that's on the
yeah, I was gonna say, this is a morphism of locally ranked lattices.
But if there's only one.
you think it should be automatic? But
Well, constructively, there's at most one, right?
Yes,
So there are cases where classically we have that, but sort of. Morphism of locally ranked lattices if for all U and S you can look at pi of du of S and that should be sort of, I didn't write, so because there's at most one D, I tend to not, so this is the support L, and this is the corresponding of M. So pi U, and here we have pi shard S.
okay, but this is now the same as the classical.
Exactly.
notion of-
So if
Doesn't have anything to
yeah,
do-
if you look at the case of a topological space, or like a ringed space, or locally ringed space where this is defined as all the points where at the stalk S becomes invertible, then your morphism of ringed spaces will be one of locally ringed spaces if and only if this holds. Yeah.
So if you read du of S as so in the case of a topological space, if you read du of S as the union of all V such that S becomes invertible on V.
Yeah.
That's what you meant. Okay.
Yeah.
But
Oh
here we're
yeah,
talking about-
exactly.
But here we're talking about these lattices, and we think of lattices that are not covariant, that do not have arbitrary joints.
Yeah, exactly. Yeah.
So
we
in that
might
sense,
not always
we
be.
can't really define the du in this way here. We have to ask that such a thing exists.
Yeah. And
Okay,
there's
but
one.
then, so
yeah.
if we could you say again what you said, Mark? You said if we think of du of S as this.
Yeah, but the question is,
Biggest
can we
open
now use the last line on the left-hand side as a definition for D and substitute it as much as we can on the right-hand side? Do we get some condition that is D-free, even constructively? Because constructively, because I mean classically it's just the usual notion of morphism of local rings star-wise.
But in which setting? In the setting of topological space and open subsets, or in the setting of a lattice?
And it's also setting of letters. I'm not sure. Maybe it doesn't work. So maybe you
No,
cannot.
yeah. So you want to say something like
du of S is all.
yeah.
Yeah.
All the V less than U such that
Yeah, something.
S restricted to V is invertible, right?
yeah, or it's like, okay, it's the supremum of all V where V is less than U and S restricted to V is invertible. Yeah. I mean, for general lattice, we don't know if this supremum exists, right? And there's
Okay, so we ask for this discriminant.
yeah, exactly. So we're given these suprema as an extra structure on our lattice in the constructive point free case.
But what is I mean, just classically, what is the formulation of the requirement on a morphism of locally linked lattice that looks most similar to this? So usually we say that the maps at stalks are maps of local rings, right? Can we say something like it looks more like this? Did you have something like that in mind?
Not in the formulated version.
Okay.
I mean, okay.
Yeah.
But probably we can say something like, what is this? I mean, it means if I have a section S and I put it back, somehow the set of points where it's invertible stays the same. In a sense that I just
Modulo pi.
have to pull this set back to,
Yeah.
right? Is that?
Yeah.
And that looks quite similar to this.
Yeah.
Okay.
So once we have this, we can define what our schemes are supposed to be. Well, it's a locally ringed lattice in this sense, where we have a finite cover of this lattice such that restricting to the elements, those will look like our constructive spec. So there's a risky lattice with the structure sheaf and the support here. Right. And we can not that much, so I have to jump over a couple of things. So the schemes that we get this way are exactly the quasi-compact, quasi-separated schemes, which is also worthwhile pointing out. And this is because lattices correspond to coherent topological spaces by stone duality for distributed lattices. And coherent means sober, quasi-compact, and quasi-separated with in the Grothendieck lingo. Quasi-separated means the compact opens form a basis of your space. So you map a coherent space to the basis of compact opens, which is exactly what we did in the case of the risky lattice. And so we can get back to our original picture and make it constructive. Way. So we get our and I'll write an op here because I already mentioned things are kind of opt, right? We think of the lattice elements as the compact opens of a coherent space. And we can define US schemes here as a full subcategory in a completely point-free way that will be classically equivalent to quasi-compact, quasi-separated schemes. And we still can define this realization functor that if you look at how you see QS schemes are defined sort of in the functor of points approach, they'll give us an equivalence disjunction or restricted T schemes. So maybe I want to use the rest of the time to define this functor. And the important notion here is that of a compact open subfunctor. So we have some presheaf X that goes from factor from commutative rings to sets, and some U, that's a subfunctor. This is said to be compact open if big commutative ring A and look at the A valued points of X. So this will be the same as the natural transformation from spec of A or unit of A to X. If we take the pullback of U here, then this will be so this will be something of the form phi okay, so we're given a B, this will be a appreciative of the form given a B, it takes B to the set of morphisms A to B's. God, I don't have enough space. I'm sorry. Such that yeah, so there's a finitely generated ideal in A such that sorry, this is a mess. So U is a compact open if for all A and A valued points of X there exist generators A1 till AN in A such that pulling back U along this natural transformation gives you the functor that sends B to the morphisms from A to B such that if you look at the image of those, they give you the whole ring. Right, if you drop the compact, you have to replace these finite generators by any ideal of I. Right. But these compact subfunctors are classified by the Zariski lattice. And we didn't have to leave it on the side stage. But so an alternative definition could be subfunctor U of X. So we said that the Zariski lattice is also this the lattice of finitely generated ideals modulo of this relation where radicals become equal. And we think of the Zariski lattice as a pre-sheaf in here that sends any ring to the Zariski lattice over that ring. Then we have sort of this map that sends the point to the top element, and then the compact opens subfunctors are exactly the ones that appears pullbacks or maps into the Zariski lattice. And so in the internal setting of synthetic algebraic geometry, those are exactly the open propositions that Matthias mentioned earlier. So what this functor does, it sends any pre-sheaf in here to the lattice of compact open, so the lattice of maps from X into the Zariski lattice pre-sheaf. And the structure sheaf is then recovered as natural transformation from U into with the representative of the polynomial rings, polynomial ring with integer coefficients. This is also just the forgetful functor from ring to set, because, well, given any ring, we just choose what to plug in for x, and this will give us one morphism. And also, once we sort of relativize, not from com rings to algebras over some base ring A, and take the polynomials over A, this will also be the very special local ring in synthetic algebraic geometry.
Sorry, so the L diagram there
Mhm.
is the
This is the
lattice of
that
the
sends-
structure sheet.
No, this is lattice that sends R to the risky lattice.
Yeah.
Yeah, so it's an internal lattice,
Yeah,
right?
right.
But yeah.
Okay, but it is all, okay. But
Yeah.
fun fact, it is also what you get when you take the internal ring lattice structure sheet and take the lattice of that.
Ah,
It is also
yeah.
internal lattice and it's the same.
Yeah.
Right, yeah.
So maybe I can sort of stop here. So what we have is a completely point-free story of sort of geometrical schemes and functorial schemes where we sort of externally see all the interesting objects from synthetic algebraic geometry. And yeah, all of this works completely constructively. One thing that's maybe interesting is what is the view where U is a compact open subfunctor and alpha is the natural transformation from here to here, right? Because that's what we also have to specify if we look into local unit lattices. Well, this will be tree sheaf that sends some ring. Right. So if we look at the A valued points of this, so hold on. Now about that forward. Well, this will just be the A valued points of U, right? Such that we can take alpha of x. Alpha of x will be some A valued point of this guy, so this will be morphism from polynomials into A, so this will just be point in A basically. So this is the unit. Right. Yeah, so everything works out very nicely and very straightforward. That's maybe sort of the moral of the story. And of course we can restrict ourselves to A algebras of finite presentation. Then we get something like locally ringed lattices over. So spec here is alright, spec of A, but I mean, of course, the risky lattice with the structure sheaf. Here we get A schemes of finite presentation. You get this the same. And
That's a quasi-comic first separated.
yeah, so I mean, in the sense that finite presentation means locally a finite presentation and quasi-compact and quasi-separate. I think that's the standard definition. Yeah. And then this will be a small category. We won't have any size issues. Then everything really works out constructively, actually. If you, yeah. Yeah, and that's where I'm going to stop. Thank you.
Okay, questions?
Yeah.
That's maybe a dumb question, but you had this L, which tends R to its service letters.
Mhm.
I'm wondering if you can view it as a subobject classifier of some topos where the subobjects of X are exactly the compact open scheme. Because just from the pullback level. Yes.
This corresponds to a subtopos where propositions are just the open propos.
I don't see a subtopos yet. I mean, so this L is subobject of the subobject classifier. But then does this check internally subtopos? I mean, I don't see how. I mean, having a subobject of the subobject classifier means that we have some subclass of all monomorphisms. In this case, it's monomorphisms that are open embeddings. But yeah, I mean, if you're looking for a subtopos, this subtopos will have its own subobject classifier. Then you can ask, does it coincide with the old one or not? Let's see how it goes.
I'm also not sure.
Yeah. I mean, think of sheaves versus pre-sheaves. I mean, the sub-object classifier of sheaves is much more complicated than pre-sheaves.
So I guess we could ask the question, is there a final topology such that the sub-object classifier for this final topology, when we forget that it's a sheaf for the final topology and just regard this object that is explicitly topos coincides with this object added? But yeah, I don't think the final topology.
Neither final nor final.
Sorry. The topology that gives us the smaller subtopos.
I have another remark.
Yeah.
At the very beginning, you said up to set theoretical difficulties.
Yeah.
But maybe this is some some advertisement for this approach. So I mean, when one takes the right hand side, I mean even before where you just have locally ringed spaces, or topological spaces, then one does not have these set theoretic issues. I mean, one can just define what the scheme is, and the scheme does not become, or the category of schemes does not become too large.
Yeah.
It is of the same size as the category of sets.
Yeah.
While when one takes the what you call the functorial approach and forget about the finally presented.
Yeah. So we go back
then,
to
then you get a category. I mean, the functor category, which looks, I mean, which is large, and so if you, and now you're trying to find your category of schemes inside the very large category, and the usual point one makes is, well, okay, essentially it's of the same size as the category of sets because you have this equivalence.
Yeah, exactly. So when you
but this equivalence was not constructive.
No.
So,
Yeah, so
in your approach, I mean, now you have a constructive proof that that the category you get from the functor point of view is essentially what would I say, moderate? I mean, it's not small, but it's not too large.
Yeah, locally small, I guess. Or that.
Yeah, but the set, but it has a
Particularly locally smaller.
Yeah,
It's
not considering something like the category of all functors.
Yeah, exactly. So I guess in a classical setting, when you are really careful, maybe have a use Grothendieck universes and have like theorems about accessible free sheaves and stuff, then you can show that this has to sort of exist by abstract nonsense, right? This is just a left Kant extension. If you think you can I don't know, but I think basically in ZFC you can't do that, right? You can't construct this. This is like really big and you
Well, I mean, you can do something sort, I mean, like kind of what Peter Scholz is doing with condensed sets. So you cut off your category of algebras or rings at some regular cardinal.
yeah.
Then you have
exactly.
then you have a category which has not, well, maybe not the best. I mean, you don't get a topos.
No, yeah.
When you, I mean, for each cover you get one, but then you take kind of co-limit or this and this. You can still do it in ZFC and essentially you end up with the right category.
But yeah,
messy.
yeah, and I think constructively we don't have any hope of doing anything like that. So yeah, also this is the constructive picture and everything, where everything looks nicely and things are of the right size and yeah.
All right. So thank you again.